All right, let's jump straight into this with absolutely zero fluff because, well, the examiner has set a nasty little three-move trap that ends up costing Cambridge IGCSE Physics 0625 students critical marks every single year. Welcome to this explainer. We're looking directly at the official exam practices for variables, fair tests, apparatus, and measurement precision. And right out of the gate, I'm going to show you how a seemingly perfect answer can absolutely tank your grade.
So check out this student answer. It's about a simple electrical circuit reading, and it is deeply flawed. The student recorded three voltage values, 3.2 volts, 3.1 volts, and 3.9 volts. To be rigorous, they calculated a mean of 3.4 volts, stating they did this to, quote, improve the accuracy of the experiment. Now, on paper, to an untrained eye, taking an average sounds like great science, right? But the examiner's red pen strikes us out completely. Bam! 0 marks.
So why in the world did this completely normal-looking answer score an absolute 0? It actually comes down to two fatal flaws. First, they fundamentally misunderstood their dataset, and second, they used a physics keyword completely incorrectly. To understand why ordinary revision fails here and how you just lost those marks, we really need to uncover the examiner's secret rules of measurement quality.
Section 1. The first quick win, accuracy versus precision. Let's fix this massive point of confusion right now.
We're looking at two words you absolutely cannot mix up in Physics 0625. In everyday life, sure, people use these words to mean the exact same thing, but in the Cambridge exam room, mixing them up is a guaranteed 0. The crucial point here is that accuracy is about hitting the bullseye, right? While precision is about hitting the exact same spot over and over again, even if it's nowhere near the bullseye. To put it simply, accuracy means how close a measured value is to the true value of the variable. Precision, on the other hand, means there is very little spread of repeated measurements about the mean or average value. Basically, all your repeated values are clustered super close to each other.
This beautifully illustrates the official Cambridge definitions directly from our source material. And crucially, precision can also just mean looking at the number of significant figures you're actually able to state from your instrument. For instance, if your voltmeter reads 3.21 volts instead of just 3.2 volts, well, it has higher precision. Now let's jump back to our student who scored 0. Remember? They said they took a mean to improve accuracy. But taking a mean does not improve accuracy. It minimizes the impact of random errors to improve reliability. They literally just used the wrong word. But hey, that wasn't their only mistake.
Remember those specific readings, 3.2, 3.1, and 3.9? They completely failed to spot the anomaly before calculating their mean. According to the official source, an anomalous result is one of a series of repeated experimental results that is much larger or smaller than the others. I mean, 3.9 volts is massively out of step with 3.1 and 3.2, right? You absolutely cannot include an anomaly in a mean calculation. It completely skews the entire result.
Furthermore, if you were to actually plot that data, anomalous results translate into outliers on your graph. An outlier is a value or point that's considered highly unusual compared with the general trend of your other values. The rules here are incredibly strict. You have to identify any anomalies, and you absolutely must exclude these values from your best fit lines and your calculations. Our 0-mark student? Yeah, they included the anomaly in their average, completely dooming their data from the start.
And all of this brings us to a fundamental reality of physics experiments, which is uncertainty. This is the range of variation in experimental results because of sources of error. The true value is expected to be somewhere within this range. Listen, every single instrument has uncertainty, from a highly precise digital timer down to a simple plastic ruler. Ignoring this variability, like say assuming that 3.9 was just a normal reading to be averaged, is exactly how you fall right into the examiner's trap.
Section 2. The ultimate examiner clue and 4-step framework.
I'm about to show you the exact examiner clue that changes your practical answers completely, ensuring you never drop these marks again. But first, you need the underlying framework that makes that clue super obvious in the exam hall. Whenever you face a practical investigation or data analysis question, you have to build your high-mark answer using this exact 4-step sequence. Step 1, identify the concept, like random error or precision. Step 2, pull evidence or data directly from the question itself. Step 3, apply scientific reasoning to connect that data back to the concept. And Step 4, package the whole thing in exact examiner wording, utilizing those strict definitions we just covered. Now, what's really fascinating here is the exact list of things that cause random errors in your experiments pulled directly from the official guidance. Measurement uncertainty depends on the precision of the instrument, like whether your meter has 1 volts or 1 millivolt divisions. It depends on the accuracy of the instrument. I mean, does it have a 0 error before you even hit start? It also depends on the nature of what's being measured, like radioactive decay, which randomly fluctuates by its very nature. And finally, it depends on the techniques and skill of the person doing the measuring. Any single one of these can introduce random errors into your setup.
Section 3. Mastering the apparatus setup.
Let's apply our framework to a classic Cambridge-style circuit setup you're highly likely to see on your paper. This shows the setup for measuring the resistance of a thermistor. Pay close attention to the details here. We've got a thermistor placed in a beaker of hot water. It's connected in series with an ammeter and a power supply, while a voltmeter is hooked up in parallel right across the thermistor. Plus, there's a thermometer sitting in the water to read the temperature. This right here is a standard high-yield exam setup.
So the big question, how do we actually minimize random errors in this specific setup to guarantee top marks? Well, our source gives us the exact protocol. First up, practice the experiment before taking real readings. Just get a feel for it. Second, as you collect your data, actively identify any anomalous results in the voltage or temperature. Third, and this is exactly where our very first student failed so miserably, exclude the anomaly. Do not use it. And finally, take a mean, or average, of the remaining repeated results. To get those top band marks using our framework, your scientific reasoning has to explicitly state that taking a mean minimizes the impact of random error on the values, but only after you've cleaned your data.
Section 4. Spot the error challenge.
All right, it's time to put your exam scheme thinking to the real test with a quick interactive challenge. I'm going to share a statement written by a hypothetical student based on that exact thermistor setup we just looked at. The student writes, "To ensure high precision in my thermistor readings, I will make sure the thermometer has 1 millivol divisions." Read that deeply flawed hypothesis carefully.
I want you to pause for a second. Look closely at that statement. Use the 4-step framework we just talked about. Think about the apparatus in the diagram. Can you predict exactly what the examiner's red pen is going to cross out here? What is the fatal error?
All right, here comes the red pen. The student completely confused their instruments and their units. A thermometer measures temperature, right? Not voltage. Therefore, the unit must be degrees Celsius, absolutely not millivolts. A thermometer relies on temperature divisions for its precision, so higher precision would mean having a 1 degree or half a degree divisions. Millivolt divisions belong strictly to the voltmeter in the circuit diagram. This is exactly how the exam tests your practical awareness. They want to see if you actually know what the apparatus does in the real world.
Section 5. The final checkmate.
You now have the framework to dodge the traps of random errors, anomalies, and mixed-up definitions. You know exactly why taking an average with an outlier destroys your score, and you know the strict difference between accuracy and precision. But here's the massive unresolved problem. You know how to fix flawed data, and you know how to identify wrong units in an existing setup. But what if the exam gives you a blank page and asks you to design a timed practical investigation completely from scratch? You'd have to build a flawless experimental table, choose the correct graph scales, list safety precautions, and state control variables all under extreme time pressure. That is a completely different beast.
Can you build a high-scoring practical design before the clock runs out? Leaving this unsolved is honestly the biggest risk to your grade boundary right now. Knowing the definitions just won't save you if you can't structure the investigation perfectly from zero.
To guarantee your success, you absolutely have to master this design phase. I recommend watching the Physics 0625 timed answer writing system walkthrough to learn the exact steps to design your own practical. And of course, subscribe to the YouTube channel Ace the Exams at acetheexams_IGCS to really excel in your Cambridge examinations. As you stare down your next blank practical paper, ask yourself, are you the student who falls blindly into the examiner's trap, or the one who builds a flawless, high-scoring design from scratch? Master these rules, ensure your final checkmate against the examiner, and I will see you in the next explainer.